is Tato Moyeng. So today I'm going to walk you through the Robots World project. So this is a brownfield project, meaning it involves building new features or updating existing one in an already established code base rather than starting from scratch. So I'm gonna introduce you to my team members. So first we have Simpiwe Liwayo, and then Tato Metanalo, David Mutsweneng, and then myself, Tato Me, and we have Catherine Okeyo. I'm gonna take you through our project overview. So the objective of this project is to update a client or server robot world application. This involves two main components: the server program side, which manages the world obstacles and robots, and then the client side controls a robot by sending messages to the server. We received and this implemented client or server architecture where the client sends requests to the server and the server responds accordingly. Yeah, so moving to the next slide. Yeah, so I'm gonna be taking you through the Git repo. So this show the correct source files are being managed within the appropriate directories. And then where we'll take you through the committee history to demonstrate the ongoing updates to source files, adherence to vision control, and how each commit message relates with a specific task or update. And then I will be talking about the vision control, the Git vision control, to show how vision control tools are used to prevent issues like simultaneous updates by different members and to protect source file from loss. Also packaging for deployment. So pipeline status. So we're gonna demonstrate how automated tools ensure the integrity and consistency of the project files, validating that the project meets the given specifications. So also we'll take you through our documentation, which is README. So the documentation was created according to the design, and that the program was developed in aligning with the plans of the project.
Good day everyone, I'll be walking you through section B of our Robot Walls project, Brownfields project, focusing on code and design alignment. Now let's begin with how our code meets the project specifications. Okay, the project specifications clearly outline the need for a world that supports robots navigating around obstacles, pits and mines. As you can see, my code strictly adheres to this by implementing features such as configuring world size, customizable obstacles, which are over here, where you would customize it by adding it as a command line argument, and handling of the robot movement that is done by our simple server. I'm just opening that, which is done by a simple server, which is responsible for reading requests and returning responses. We have a multi-server handler that's responsible for editing for our server console commands, so you might need to change, maybe configure a world, maybe read world from a database, and yeah. We made sure that we meet all of the protocol requirements that were needed for our project, like our different commands, our launch command, our load command states, etc. And we also have default commands. These are our movement commands, including our turning and our going forward and back commands. Right. Next, I'm gonna go into how we went about accessing our data. Right. Now, okay, let's talk about the data access. The world data, including our obstacle payments, is stored and managed in an SQL-like database. Data accessing is implemented using the repository pattern in conjunction with the data access object pattern. This allows for efficient interaction with the database, ensuring that operations such as saving and storing worlds or managing robot states are performed reliably. Okay, now how we did that is, okay, let me start with the multi-server handler, which will read our console commands. Now with that, we have commands such as restoring. You also had to include the name, displaying, which will just display all the words in the database. We have delete, will delete our database, and yeah, those are the commands that we need. Oh, and save, that will save our world that we have, with including its obstacle placements. Now how we do that is, my other teammates will explain how actually they go about implementing all these crude details of the database. Now, for example, over here I have a world DAI class that's abstracts the like the underlying database calls, ensuring clean and modular data management in the code. When it comes to our naming conventions and clarity, as we look at the code, you'll notice that the naming conventions are intuitive and descriptive. Classes like our world, obstacle, we also have robot, and world DO, world DAI. They clearly convey their purpose, making the code easy to follow. Okay, for instance, save world does exactly what it says. It saves a world into the database, which world exists. Will handle like logic and make sure that our world exists, that we can't just like access a world that doesn't exist, right? And then our conformance to design documentation. The documentation conforms to the initial design documentation with only a few deviations. For instance, I initially planned to integrate the web API, which is another data access method, where you would use API HTTP request and then get an HTTP response with a JSON that will outline that will show us the objects in the world. That maybe if you were to send just world, you would send a HTTP request with just world, you will get the objects in the instance of the world, and we also have world name, which will get the objects in a world that's stored in a database. Okay, initially I planned to integrate the web API layer directly into the robot world server. However, for better modularity and maintainability, I decided to separate them. This decision was made to allow independent scalability and testing of the API and the server. Okay, these deviations are thoroughly documented with reasons in the design docs, which is our wikis. Now I'm gonna get to testing. Okay, now to ensure the robustness of the system, right? We developed a comprehensive test strategy. This includes unit tests for critical components like robot movements. These are over here, okay, and obstacle detection, as well as integration tests to ensure that the server communicates directly with the database, which are found in here, like our launch robot test, which is an acceptance test. Now, our strategy for our acceptance test and sending requests and maybe getting the correct responses, we start the server with the specified configuration if it is needed, right? By creating a start server function. Now, once we've started the server, we have a loop that just makes sure that our server is online, because it might take some time for our server to actually be online. We use localhost because at the moment, we're just using our own PCs. And then after we send a request, as you can see, we're just going to send a request, and I'm going to receive a response, which is a JSON node, and then we'll just make sure that we receive the correct responses. Okay, we've also designed some stress tests to simulate like high robot traffic in the world. like over here, where with our world is full, where we push as many obstacles until we get an error that says no more space in the world. Now this will assess the system's ability to handle concurrent operation without any failures. The tests are automated using some of the tests are automated using a framework like we have Mockito in our some of our unit tests. For instance, you'll see tests validating that robots are successfully placed in the world, that they avoid collisions, and then the system can restore previous world states correctly from the database. These results help in identifying edge cases and improving the code base. Now, how we make sure that every time any changes that we made, as we have created a pipeline for our code. Over here, we have the pipeline for code. Can I just open this? Which will run our build job, make sure our code is always compiling, which will run our test job, which will run our unit test, our package job, which will package our code maybe for release, our acceptance test job, which will make sure that our acceptance test pass, our release job, which will release our code, we use the release for the Docker job, which will publish our code onto the container registry, which it is published. As you can see, this was our last push. And then it did publish our acceptance test. Moving on to user compliance, I've designed a project with user specifications in mind. The server has a user-friendly server, allowing clients to interact with the world via simple HTTP requests, such as our get world over here, which will get different kinds of world or post Robert and the name, right? The user can easily configure world size and obstacles, ensuring that the program adapts to their needs. We've added that into some of our documentations in our README. Over here, we've shown how you can run our server and be specific on your port, the size of your world, and maybe add one of the obstacles that you might need, right? User instructions and our basically minimum disruption installation. To make the project easy for users, clear instructions are provided on how to interact with the API and the robot world. This readme.md, it contains step-by-step guides. Over here, for setting up the project, launching the server, and using various commands. As you can see, the installation process has been streamlined to minimize disruptions, with Docker packaging provided as an option for user deployment over here. Okay, now finally let's look at the documentation. The README not only outlines the project purpose, but also includes a detailed description of the code structure. Each class and method is documented to help other programmers understand the logic behind the implementation. Okay, this wasn't done here, this was done in the wiki. There's also a section dedicated to explaining the various tests that can be run on the system, which will be set by my other teammates. There's also a section dedicated to explain the various tests that can be run on the system, the purpose, and how they can be extended to cover additional cases. In conclusion, our Robert Dolls Bronfels project adheres to the specifications and design documentation with clear naming conventions, robust data access methods, a comprehensive testing strategy, and detailed user and developer documentation. Thank you.
For database management systems. So we will start with the problems that are represented by database management issues, and here are some of the common database management issues. So with data inconsistency, the problem is that it occurs when different versions of the same data exist across multiple databases or systems, leading to confusion or errors. And then there's data redundancy, and the problem with data redundancy is that it involves a lot of storing of the same data in multiple locations, which can waste storage space and lead to inconsistencies. Customization, as well as flexibility, potentially requiring custom development for more complex or unique data entries. And then another example of end-user tools is a graphical user interface. Most database management systems provide a user-friendly graphical interface that allows users to perform tasks such as data entry queries and reports through menus, buttons, forms. Graphical user interfaces simplify interaction with database, making it accessible to users who are not familiar with SQL or other query languages. Query builders. Query builders are graphical tools that allow users to create and execute SQL queries without writing code. Users can select tables, columns, and conditions from a visual interface, as you can see here. So, implications of this are performance issues, the edge or complex queries, as the query builder may not always create the most efficient execution plan. Right. So the motivation for choosing a database management system for the robot project. In our robot world project, the choice of a relational database management system was motivated by several critical factors. Firstly, the project requires saving and restoring the map of a robot world, which includes structured data, elements like obstacles, pits, mines. A relational database management system is well suited for this purpose due to its ability to handle complex data relationships using table rows and columns, primary keys, and foreign keys. The database management system ensures that our data is well organized, easily retrievable, and consistently maintained across different entities. The requirements for database access. The requirements in our project are primarily driven by the need of efficient data storage and retrieval, and a database management system must allow us to store various components of the robot worlds. The use of SQL as a standard language for interacting with the database ensures that we can define, read, manipulate data effectively within our Java application. Additionally, the database management system should support seamless integration with Java, allowing us to use the Java Database Connectivity JDBC API to connect with the database. The primary objectives for the database access in this project are to ensure data persistence, consistency, and integrity. We need the DBMS to efficiently handle transactions related to saving and restoring the robot world, ensuring that no data is lost or corrupted. The performance factors include the spread of data retrieval and updates, the ability to handle concurrent access by multiple users, and the robustness of the system in maintaining data integrity under high loads of data. Atomic, consistent, isolated, and durable transactions, which ensures that all changes to the data are performed reliably. This is crucial for maintaining data integrity in scenarios where multiple operations need to be performed as a single unit. This is the reason for our choice. This is our ERD model, and it shows you that the world has its own table, the pit has its own table, as well as the obstacle, and the mine has its own table. The world is a primary key which links to each foreign key in the obstacles and pits and mines table. As you can see, they all have world ID as the foreign key, world ID as the foreign key. Each table has its own primary key, which is an ID that will show its uniqueness as well as link it very well to our Robot Worlds project. This code is a Java class named Database Connection that handles the interactions with an SQLite database for managing world data such as obstacles, pits, and mines, as you've seen in our ER diagram. The Database Connection class establishes a connection with SQLite database using a JDBC URL. It initializes a world DAI class interface which provides methods to interact with the database and ensures that the necessary tables such as world table and mines exist. You have the initialize function which instantly creates the tables for our world mines every time the user interacts with the world. We have the save world function which allows you to save a world with your unique name, its dimensions, and any obstacles associated with it, such as pits, mines. It checks if the world already exists to prevent duplication, and it inserts the data into its appropriate tables. Then we have our function for restoring. This method retrieves a world and its associated elements from the database based on the world's name. It returns a map containing the world attributes and associated obstacles, pits, and mines, effectively reconstructing the world in memory. In closing, this class is responsible for managing the database related operations within our Robot Vaults project by saving, retrieving, and deleting data. It also ensures that the database structure is set up correctly and that the data is handled effectively and safely.
Hello everyone, my name is Motlalepule Catherine Okewo, and I will take you through evaluating SQL implementation and data management in Robot Vaults project. In this section, we are going to discuss SQL and how we use it to create tables and organize data in our Robot Vaults game. We use SQLite to save and delete world configurations, then restore the worlds with obstacles. The aim is to demonstrate how SQL facilitates efficient data management in the Robot Vaults project. The first one will be implementation of program design using SQL. This code from our World DAI interface shows how the program design is implemented using SQL. The SQL command inserts a new world configuration into the world table. This aligns the application's design with the database schema, ensuring consistent data storage and retrieval. So in our world, we are inserting our data into the world table. The other one will be understandable SQL code. The get world by name method is a straightforward SQL query that selects specific columns from the world table. The clarity in naming conventions and SQL syntax makes it easy and understandable. The next one will be commented code. The code is well commented, explaining the purpose of the SQL operation. Commenting improves code readability and helps other developers quickly understand the functionality. On our code, we commented the below code so that you can understand what's happening. We are inserting a new world configuration into the database. The next one will be preserving data integrity. This SQL operation ensures that deleting a world does not leave orphanage records in related tables, preserving the data integrity. Proper constraint and transactions are essential for maintaining data consistently in multi-user environments. The other one will be how we optimize the SQL query. The SQL query retrieves only the necessary world ID, optimizing performance by reducing data processing overhead. By limiting the selection to a single column, the query is efficient, especially for frequent operations. So in this query, we are selecting only the world ID from our world, where the name of the world will be whatever that you've saved. It is the name of your world. And then going to making SQL understandable. The query uses descriptive column names, which is X position, Y position, that clearly indicates the purpose of each field. This approach enhances the readability and understandability of SQL code. Moving forward to method of accessing data. This method exemplifies how data is accessed from the database using SQL. The query retrieves all details of a specific world, demonstrating a typical method of accessing data in the application. So on our code, we are retrieving everything, every data from the world where the name of the world equals to whatever the name that you've saved. If you saved cat, then we are retrieving every data from that world. The next one will be good use of data sharing. This method shows how data sharing is managed within the application. It ensures that new world configurations are consistently saved and available across different parts of the application. So in this snippet, we are saving our configurations into our world DAI where we inserted our world. The last ones will be linking database and website. This query retrieves world names for display on the web interface. It illustrates how the database and websites are linked through SQL query, which is vital for dynamic web applications displaying database-driven content. And the last one will be linking web pages to back-end application. This method exemplifies the connection between a web page where users input world details and the back-end application that processes and saves these details in the database. This integration is crucial for responsive and functional web application. Thank you. I will give to my team member to continue.
Brownfields section E, which is based on testing. We'll be assessing our testing plan and execution of our testing plan. This will include database access verification and computer program testing, and we actually included testing functionality of our program unit test, coverage of our tests, and performance test, and we have a database test as well. And we also have usability test case, of which we call them acceptance tests. And we have integration tests, which allow us to actually integrate systems, for example integrating the database API to our system. So I'm going to take you through our test plan, of which we administered it via GitLab. So if I go to our GitLab, I have a story. So we used the issue board on GitLab, which allowed us to use a ticket system. So this ticket system allowed us to actually develop using the Agile method. So here I have an example of our test plan for our launch command. For the heading of the test plan, which is launching a robot. So, and a brief explanation of the 10. We have scenarios. These scenarios are our edge cases. So our edge case 1, launching a robot command should be successful, and an incorrect launch command shouldn't be successful. When you typed launch incorrectly. And we actually included stress testing inside our acceptance tests, of which we're launching launching more than one robot. To actually dive deep into a scenario, see here is the scenario. So scenario 1, launching a launch command should be successful. So given that I am connected to a running robot world server, and the world is of size 1 by 1, so in this case the size was 1 by 1 because of the jar file that we were given. But as the development went by, the size of the world, actually you can configure it by a user can configure the world. This launch command should actually allow the robot to be launched into the server, and we should get a valid response from the server, and the position should be random, and we should get the state of the robot. And let me take you through our code, whereby I explain more on the launch, so more on our tests. So before I delve deep into the testing part, so we have a dependency which allows us to actually connect to the database. So this dependency, it has a jar file, whereby this jar file is passed here on the artifact ID. Then this will allow us to actually connect to the database persistently, even when it's not updated on the repo. So yeah, we just attach the jar file. So I will take you through our protocol test, of which is our acceptance test. So I will go through the launch test. We had an approach on how are we going to actually launch the robots into the server. So we had to automate the server to actually start, and robots will start joining the server and creating the obstacles. So here we have a method here that starts our server, which takes the port and the size and obstacles as well. So these are the arguments over here, and we use the process builder to actually build the process to start our server. Then we allowed our server to halt a while, wait for the robots to actually launch into our server. And when the server is actually online, then they can join. Now I'll take you through launching a valid launch command. So here what we did, we're starting up our server and give the port of the server and the size of the world and obstacles. So here we actually sending a request to the server, given the robot name and the command, and we get the response back. So this response back is actually that we're going to get using the field results. This field results has data for our position of the robot, and and the number of the robots. Then once the response has properly passed, it will send OK, and once the response is OK, then that's when we can assert it to not null. Then it will get the state of the robot. Then that's where we close our server. And I'm going to show you another acceptance test whereby we launch two robots. So when we launch two robots, we have to remember that we give them different names, and the request launching the robot 1, which is a HAL, and the request launching the robot 2, which is R2 and D2, and same applies here. We get a response from the server, and we get the results and the state of the robot. We assert the state and everything. I'm going to run the acceptance test here. So I'm just going to use our pipeline editor here for our acceptance test jobs, just to to make sure that we run proper tests that we are looking for. I'll run them here, since this is the same directory. We add the home directory, and we on the project brownfields and the robot worlds. So on the acceptance tests, they are running. Then there we go. So this is where they start running. So the reason why the world command, the reason why when we get to test it stops, this is the time constraint, the thread for time constraint that we gave to the server to wait for a robot to connect, and the APIs to connect as well for tests. So here I'll explain a bit more on our test. So this is the world command. So the world command actually just gives us the world configurations and all of that, and it started to run, and after running the world command, the test passed, and we run the save world test, of which is our database. So over here, it actually shows that it is connected to the database. So the database API is working, and you can find it on our source database. So that this is where it starts connecting, and after connecting, it will check if the world exists or not. Then it will start creating the world if it doesn't exist, and the pits and so on. And we have restore world as well for our database, and it's still running. While it's still running, I'll dive into I'll actually show more of our acceptance test for database, since I was explaining how it is connecting to the database, and all of that. So the logic behind this, we actually took the database object to actually get the database. Then before we actually start the database, we have to get the database URL, of which we are using the acceptance test database here is created, since we were running it here on the terminal. And if you can check, it has created the fields for mine, object, pits, and the world. And restoring the world, then after giving it the directory to connect with our database API, that's when we can start testing. So this is the test that is responsible for restoring multiple worlds. So as you can see, we used a string array whereby we just pass different types of world to restore and their configuration here. This is where we start connecting the database using using their name. So then we start saving the database using their name, of which is the unique key for our database. Then once it is restored, once we have connected, this is where it will start to asset. This is where it start assetting. So here we're using a map to restore the world. Then we get the world, we get the string, which is the world name, and the object, which is the object class for, since I did name it here in the database. And this is where we start testing. So this is where we pass the world that we restored. Then if there is no world, it should be null. Then if we have the width and we get the width of the world, and it's going to match the world ID, of which is the world name. And and let me check if the acceptance tests are done running. So our acceptance tests are done running, and it has restored and created mines, of which is a mine command, and the forward test command, and the loop command, and the launch command, and the state command. Then all our tests are running properly. So we have 23 acceptance tests, then all of them they built successfully. So if we actually want to run all our test cases, all the tests did run. And here's the back command. So we have 4 tests that are running for the back command, and we had 0 failures. Since I did say previously that when you want to run all the coverage for the test, you have to run Maven. That's about it. Thank you.
Evaluating documentation consistency and design adherence in computer program presentation. So, in system development, documentation is written information that explains how a program or a system is being designed. So it includes guides, technical details, and comment in a code, helping developers and users to understand how the software works. So a good documentation is important because it makes sure the system can be used and fixed and improved over time. So it also helps the team members to work together and share knowledge. Documentation that we have implemented as a group, it's a README and Wiki and Java docs. So as I show you, I'll start with the README. Here's our README. So here's our wiki, and then here's our Java docs. So we created a detailed documentation that includes again a README and a wiki and a Java docs. All we follow our original design. So these documents clearly follow the plan structure. So to ensure everything was consistent. So the README provides a quick overview, And then the wiki gives details explanation, and then the Java docs offers technical details. We made sure these documents accurately reflect the current state of the program to avoid any confusion between what's written and how the program actually works. So we followed a clear plan and agreed on standards to make the documentation easy to understand and use. During our review, we checked that all necessary details were covered and that everything was organized well. So this makes sure that anyone using or working on the program in future will find the documentation helpful and reliable. In conclusion, our project documentation ensures that the system is easy to understand, use, and maintain. This foundation will support future development and collaboration effectively. I'd like to thank you for your time.